Hello everyone, welcome to the lecture series of computer vision. In today's class, we see the geometric transformations, which are highly applied in motion estimation and object tracking problems of computer vision. So what are these geometric transformations? Why do we have to study them? For example, we have an object in our environment. So I am seeing or I am visualizing the object in the environment. Let it be a football or a basketball for suppose. So initially I have found my basketball at some location on the ground. After 2 or 3 seconds, at the same exact location, I cannot able to find the ball here. Why? Because the location of the ball got changed here. That means, can I say there is a transformation of the coordinates of the ball had got changed. That means the ball here had underwent some kind of a displacement, which may be an angular displacement or a linear displacement here, right? That means here let me assume the spherical ball is being captured by our camera. So finally we are getting an output image, which is nothing but a 2D image. So this 2D image is having the pixel data of that ball. Whatever we are seeing directly, that is a 3D object. So this 3D object is got converted into a pixel data, that is a 2D coordinates, right? Now can I say that whatever the thing I am getting here in the image, it is nothing but a 2D coordinate system. Okay, a 2 dimensional coordinates I am having in the image. So whatever I am seeing, visualizing, that means the ball what I see here, it is present in a 3D environment. That means it is present in a 3D space there. So definitely each and every point on the object, that is a ball, is having its own coordinates. That means, can I say it is a 3D coordinates? Each and every point on the ball is possessing a 3D coordinates. So initially the ball was in some location. After 2 or 3 seconds, the ball is getting displaced to some other location. That means it is getting transformed. So that means the ball is undergoing a 3D transformation, and the same can be visualized in the image plane as a 2D transformation, right? So what exactly the transformation is? Transformation is a process of modifying and repositioning the existing coordinates. So it may be a 3D coordinates or it may be a 2D coordinates. So these transformations are of 5 kinds. What are they? They are translation. That means the coordinates or the point or the pixel may undergo a translation or a rotation, scaling, reflection, as well as the sharing. So let us see one by one on about the each and every kind of the transformation. So the first one here is the shifting operation. I do have here in the 2D transformations. So I am having a point P that is present at x comma y location in my 2D space, that is xy space. So this point P is translated by a displacement of x naught y naught. So it is translated by a displacement vector, that is x naught y naught. So what will be my new point now? The new point is denoted by p dash, and the coordinates of this new point is x dash and y dash. So if I would like to represent the new coordinates in terms of a old coordinates, what I will be doing here is, first thing, I will be writing the coordinates in a vector form. So that means here I have taken them in a column vector. This is P is my old coordinate and P dash is my new coordinate. So these are the coordinate values, that is x, y, and here it is x dash, y dash. So what is the translation? That means what is the amount of displacement? What is the displacement vector? It is x naught, y naught. So here T represents, it is the translation vector, and the translation operation can be written also in the matrix representation. So if I see this one, I am making it sense that it is in matrix notation, right? Okay, so the new coordinates x dash and y dash equal to x plus x naught y dash equal to y plus y naught. The same thing here happened, right? Nothing have been done here, just whatever the thing that is happening is being represented in the matrix representation. That's it. Now, so I can also represent this matrix representation of the new coordinates in this way also. So x dash y dash equal to 1 0 x naught 0 1 y naught x y 1, and this kind of representation I do call it is a asymmetric expression. Okay, so previously it is only a 2D form. It is, that means a pixel is in 2D representation. Now can I say some kind of a 3D representation is there here, because xy one more new coordinate is also added here. Okay, so why I am calling this kind of representation as an asymmetric expression is, so the transformation matrix whatever I am having here, it is not a square matrix. If I would like to make this one as a square matrix, means entirely my expression, this expression is turned into a symmetric expression. How it will be? The same thing had been given here, had been presented here. Before it, in a homogeneous coordinates, a third coordinate is added to a point. In fact, each point can be represented now by a triple. So xy1 is nothing but it is a triple. So we can represent the point xyw as x by w, y by w and 1. So the triples of coordinate represents points in the 3D space. Okay. Now, so what this expression is nothing but the first one, whatever here I am showing here, right? This is the result of the before expression. That means this expression as well as this expression both are same, but it is an asymmetric expression. If I would like to make into a symmetric expression, means what? I am going to add one more. That means we can represent the xyw as I have added one more coordinate here. So like 1 0 x naught 0 1 y naught 0 0 1. So one more coordinate had been added here. You can see here this one. So now entirely this matrix is in the form of a symmetric expression. So the symmetric expression for this above matrix system is this one, because this is an asymmetric form. This is my symmetric form, right? So this is about the 2D transformation shifting operation. Now let me discuss about the rotation operation. I am having here a point P which is initially at x comma y location. So I would like to rotate, so let me join this point P with origin, right? That is at 0 comma 0. Now what I am going to do here is I am just rotating my point P, that is which is at x comma y, by an angle theta, that is in clockwise direction. So before that, this P, that is x comma y, P which is at x comma y is alpha angular displacement. It have done alpha times of angular displacement with the original x-axis. So that is why the point P is situated here. Now what I am doing, I am just rotating my point P by an angle theta in the clockwise direction. And we are also assuming that this theta is less than alpha. Alpha is what here? It is a initial angle made by the point P away from the x-axis, right? So in the clockwise direction I am going to make a rotation now. So previously, can I write my x as, if I assume the distance between the point P and the origin is r. So according to our basic mathematics, we know that x equal to r cos alpha, y equal to r sin alpha. Now what is happening? We need to find about the new coordinates. Those are x dash, y dash. So x dash and y dash are given by r cos, the same r cos alpha, minus theta, because it is moving towards the x plane here. So it is moving towards the x-axis. So that is why I am reducing with theta degrees. So r cos alpha minus theta, that means r cos of a minus b is nothing but cos a cos b plus sin a sin b. So after substituting the r cos alpha value as x and r sin alpha value as y, ultimately I am going to get the equation as x dash equal to x cos theta plus y sin theta. Similarly, y dash I am yielding it as y cos theta minus x sin theta. So the same thing I can represent even in the matrix representation, that is x dash y dash equal to cos theta sin theta minus sin theta cos theta xy. Okay, so the transformation matrix will be this one. So this is because of this transformation matrix, this is for mainly for the rotation operation. My point is being, which was at x comma y, is being translated to a new point. That means it is rotated, right? So the next one is the scaling operation. Now a point, there will be a point is scaled by a factor sx. Now there will be a point, let it be x comma y, and that point is scaled by a factor sx and sy along the x and y direction, let it be. Scaling means what happens here? If I am having initially a point, that is, let me, I am having a point that is present at 2 comma 0 initially. So if I would like to scale it up by 2 units, so what I will do? So my new coordinates will be 4 comma 0, right? That means I am scaling it up along the x direction. So the same case here we can pursue. We can consider the case of scaling of a point by a factor sx along the x direction and sy is along the y direction. So respectively, in matrix form, the scaling operation can be represented as x dash equal to sx 0, sx into x plus 0 into y dash equal to 0 into x plus y into sy. That means, can I write that x dash is equal to sx into x, y dash equal to sy into y? That means both here the original x coordinate as well as the y coordinate had underwent some scaling. Some scaling is being multiplied with x and with original y. Ultimately, I have got here a new coordinate. So this is about the scaling. Sometimes what happens, there won't be any uniform scaling. So that means only one coordinate will undergo the scaling. The remaining coordinate may not undergo the scaling. So these type of scenarios, we call them as the shearing. That is, shearing is nothing but only one coordinate is undergoing the scaling, not the every point on the object is going. So shearing parallel to the x-axis can be represented as, so here the shearing, it is parallel to x-axis because scaling we know, right? And so as shearing is nothing but only one coordinate has to undergo the scaling operation. So here y dash, whatever the previous y, the same y is also, it is replicated in and the new coordinate also. The same value is replicated in the new coordinate. That means here y is not undergoing any scaling operation. But if you see here the x value, the x value is scaled up by some units, and we can see here a new x in the form of x dash. So x dash equal to x plus ky, and this is nothing but shearing has been done parallel to the x axis. So because y axis remain constant, so y value is here same. The same thing I can also represent it in matrix rotation. How? In matrix form, x dash y dash equal to 1 k 0 1. So this horizontal diagonal, this diagonal is important here. So this one and this one in the sharing operation, so the diagonal elements will be 1. and the element which is not undergoing the sharing is 0 here. So here y is not going any sharing. That means y is not being scaled. So what will be the hyx value here? That means it is 0 comma 0, 0 comma 1, 1 comma 0 and 1 comma 1. If I assume in this manner, so as y is not undergoing any sharing, that means k equal to 0, right? Because y dash equal to, if I assume y dash equal to y plus ky, or k, otherwise instead of k, let me go with y dash equal to y plus mx, y dash equal to y plus mx. So here m is equal to 0. The same thing you can observe here. But coming to here, x dash equal to x plus ky. So here, as if you have 0 here, it means y is not undergoing any change. So whatever the new value of y, the same will be whatever there is in old value, the same will be forwarded to the new value of y. So this is about scaling as well as the sharing. So yeah, I would like to explain a bit more about the sharing now. So as I have said you, right, that means here during the operation of sharing, the diagonal elements will remain 1. So the same thing happened here, right? The diagonal elements are 1 here. So 1 and 1 hx, because here x is undergoing scaling, hy it represents y is undergoing scaling. As in the previous expression, hy value is 0. That means y hadn't undergone any scaling there, right? The same thing can be seen here, right? Okay. So this, if I would like to make, I would like to convert this one, that means into a homogeneous coordinate system. What? I will add one more coordinate simply. So I would like to translate this 2 by 2 matrix into a 3 by 3 matrix such that the expression will be converted into a homogeneous expression. Like I have shown you in the example of the shifting operation here. So here I am having something. If I would like to make into a homogeneous expression, means I am adding here one more coordinate. Similarly, that means the transformation matrix here got changed. So it is got changed here. So and this is the new coordinates are converted or represented in a 3D. Third coordinate is added such that this each point now, that means x dash y dash 1 is equal to this transformation matrix into xy1. So this transformation matrix is nothing but it is giving some homogeneity for the expression. So the same thing, this matrix 2 by 2 is converted into a 3 by 3 matrix such that it is in homogeneous coordinate system. Okay. Now it is what it is scaling. Scaling is x or y, both have to scale up or down. But coming to sharing, here only one thing is got shared. Y is remaining constant, because if you observe here the figure, the y is present at this point. Still the value of the y didn't get changed here as well as here. But coming to the x had undergone some kind of a scaling, some scaling up or scaling down. So that is why only one coordinate had underwent scaling. We call it as a sharing. So that means it is the 2D transformation sharing concept. Okay, we have one more kind of transformation, that is reflection. So I have a point here in the 2D space. This point is being reflected. It is a mirror image for this point. This point is the mirror image for this point. That means here x is not changed, only y got its mirror. That is y dash. This is the y dash, right? This is the x dash and y dash, and this is xy. This x dash that doesn't change here. Y dash had underwent. That means a mirror. It is underwent a mirror to its original value. So what happens here, or if the original value of this point is some 2 units, the new value of this point is -2. That's it. So these all are about the 2D transformations. And coming to here, we have a concept that is, suppose if I want to rotate a vector, because let me assume this is the point P, which is indicated here, and the origin of the 2D space is present here. Okay, if I want to rotate a vector at an arbitrary point P, so I want to rotate this vector. I may rotate here, or I may rotate in this direction at an arbitrary point P. Okay, let me assume like that. Okay, then what I will be doing, I do to translate the vector point P. This one is being translated, P is, this point is P is, this vector is translated to origin. That means some shifting operation had happened, right? Okay, next what I am doing here a rotation operation. So now the vector is starting at origin. Now I am doing what? My requirement. What is my requirement? Doing the rotation is my requirement. So let me rotate this vector in the clockwise direction. Yeah, done. I have rotated. Next, after that, I will translate this vector to its original point. That means I will be translating back this vector to its original point P, such that means what I am doing here, the point at origin is returning to its original point. What is the original point? This is my original point. So if I want to perform the rotation operation here. So first thing is, I have translated this point to origin. I rotate. Now this is the one what you can see. After that I have done the rotation operation. That means my task is completed. Now this vector is again rebacked to its original point. That means from 0, 0 to it is again replaced to its original point, that is P coordinate at P location. So this is how, that means here what I am doing finally is the complete operation I am explaining here by using this expression. That means first it is undergoing some translation, next it is undergoing some rotation, finally it is again undergoing the translation in the reverse direction. Because my task is completed, again I have to go back to my home, right? That means the translation is in reverse direction. This is what happening here. So the sequence of rotation is happening, translation, and the scaling matrices is called the affine transformation. So what is this affine transformation means? So actually it is affine transformation is one more new terminology in the geometric transformations. So this affine transformation is the result of whenever a vector is undergoing a rotation, translation and scaling. Okay, so the sequence of rotation, translation and scaling is called the affine transformation. So what is the matrix representation or the matrix format? So whenever we see this matrix, okay, so that means we should assume it that the coordinate is undergoing all the transformation. So what are the transformation the coordinate is undergoing? Translation, scaling and rotation. So the order of it, that means which one will come first and which one will come next, I will explain you after the 3D transformation. So affine transformation is nothing but TRS. You need to remember as TRS, that is translation, rotation and scaling. So this is about the 2D transformation discussion. Let us have a look on some problems here. This is an object present in 2D space which is having its own 2D coordinates A, B, C. Now what is the thing have been asked in the question? Apply the reflection on the x-axis and obtain the new coordinates of the object. So reflection means only y coordinate will be changed, x coordinate remains the same. You can see it is the basic mathematics geometry. A, this is A, only the y coordinate is being reflected like this. That means reflection is happening, A is reflected on the x-axis. So in this manner, similarly C is reflected on the x-axis, B is reflected on the x-axis. That means y which were having a positive values in the earlier case are now with the reflected values, that means a negative values. This is about 2D reflection. Now what about the 2D rotation? So given a line segment, because let me assume this is a vector, a line segment with starting point as 0, 0 and ending point as 4, 4. This is small o. Apply 30 degrees rotation in anti-clockwise direction on the line segment, this one, and find out the new coordinates of the line. So during the time of discussion of 2D transformation rotation, the transformation matrix is quite different with the transformation matrix what you are seeing here. Why? Because in that case the transformation matrix is the result of clockwise direction, but here in this case the transformation matrix is the result of anti-clockwise direction. So you people should be cautious. So how to obtain the new values here? So this will be my transformation matrix. I am having my old coordinates in this manner, substituting the values of old coordinates as well as the angle. Finally I am going to get my new coordinates as this one, x new and y new, as these two are the values. So next is scaling example. So I am having a square object in my 2D space with its own x coordinate and y coordinate. Every point is having its own unique x and y coordinate locations. Now what I am doing here? So scaling is done such that it is scaled twice, that means 2 times towards the x-axis and 3 times towards the y-axis. So 0. So 0, 0, this is a coordinate. This is 0, 3. This is 3, 3. This is also 3, 3. Now what I am doing here, 2 times I am scaling along the x-axis and 3 times I am scaling along the y-axis. So x-axis is scaled twice. That means 0, 3 now got become as 0, 6 because it is scaled twice. I am talking about DC line. Similarly 0, 3 which was here AD line, now it is being scaled 3 times. No, it is having the length of 9 units. Okay, so as this is a square, so if it is 0, 6, of course it is a square, but we need to consider it is a closed polygon which is of 4 sides. So 0, 6 I have to take a parallel line like this, and for 0, 9 I have to take a parallel line like this. So finally I am going to obtain my coordinates of new 2D space in this manner. That is, after scaling, the resultant coordinate will be in this manner, where we have an object which got scaled by some units along the x-axis and some units along the y-axis. So this is about your scaling example of 2D transformation. So let me give you a question. I have an emoji in this 2D space in the left half side. I have other emoji in the 2D space in my right half side. We need to determine what type of transformation the object is going from image 1 to image 2. Right? That is the question. So in order to solve the problem, we need to consider some key points of object. This is the object. In image 1, I am having an eye here. So at the center, let me mark it as some key point, and some here place a marker at this point and place the marker at the border of the tongue, one more marker as the key points. So these three key points are having at particular locations in my xy space. Now you observe the same key points where they are getting shifted in this new image. So based on that one, I can sense that what type of transformation my image in this here had underwent such that the resultant image is this one. Okay, so this is about the 2D transformation. So next there will be also a 3D transformation, like any object in the environment, definitely it is possessing its every point on the object possess some or represented by some 3D coordinates. So all the 3D coordinates, all the 3D points are converted into a homogeneous coordinates. So x, y, z is a 3D coordinate. If I want to convert into a homogeneous coordinate means additionally I need to add one more coordinate here, that is x, y, z and 1. So translation of a point in homogeneous matrix form is given by, because we have encountered how to know or how to do the 2D translation, that means 2D shifting. So x star, y star and z star, because it is a 3D transformation, or that means definitely a 3D coordinates will be present. So there will be a transformation matrix like this, and this is xy z1, and it is an asymmetric expression. Of course, x0, y0 and z0 are nothing but they are the displacement vectors only. So finally, the translation of a point is given by x star equal to x plus x0, y star equal to y plus y0, z star equal to z plus z0. Anyhow, I didn't represent it here, keeping in mind that you got an idea about this 2D shifting here. Yeah, here you can see, right? Keeping in mind that this is the one I am representing there in the 3D coordinates, but here this is my 2D coordinates. So x dash and y dash I am having here 2D coordinates. The new 2D coordinates, which is the shifted version, which is the translated version. The same thing, the same asymmetric expression I have produced here in the 3D space. So I am having here 3D coordinates. This is my translation matrix or a vector, and this is my original coordinate point. Anyhow, this is my asymmetric expression. To make it an symmetric expression, what I will be doing? I will be adding one more point here, right? That is x star, y star and z star. And one more point is what? 1 is added here such that this matrix will be changing its dimension. So previously it was 3 by 4, now it got turned into a 4 by 4 dimension. So it is a unified expression now, because it is the translation matrix or the transformation matrix here, it is a square matrix. So this is about 3D transformation shifting. Now what is the 3D transformation scaling? The same thing whatever I have discussed in the 2D transformation scaling, like we have seen there sx, sy, right? Here we need to add one more coordinate, that is sz. So this will be my extra additional thing to be added in the matrix form. So sx, sy, sz and 1. So this is nothing but the scaling parameters in the x direction, scaling parameters in the y direction, scaling parameter in the z direction. So the new coordinates will be the scaled version of your old coordinates. That's it. So 3D transformation rotation matrix. So we have seen about the rotation matrix in the 2D coordinate, 2D transformation, the same thing in the 3D transformation. So here I am having x-axis, y-axis, z-axis. Rotation around z-axis like this. That means where x and y coordinates, those are changing. No, they are not at all changing. Because why they are not at all changing means, let me consider some cone disk is present at this point. Now what I am doing, I am just rotating the cone, or I am making my plate or my disc, of which disc, cone disc, rotating around the z axis. That means the x and y plane, the x and y coordinate of this point will never change. Only the z coordinate will be changing, because it is the result of rotation in a plane which is parallel to the xy plane. Because here I said you right, there will be a disc, cone disc. That cone disc is only undergoing some rotation around the z axis, hence x and y plane remain constant. So it is rotation around the z axis, which is the angle here I am having, theta. Rotation around the x axis means alpha. Rotation around the y axis means beta. If I have rotated my disc around y axis means I am doing the rotation parallel to zx plane. If I am having a disc and I would like to rotate around x axis means I am doing the operation which is parallel to zy plane. Okay, so here by using this statement, let me see how the transformation matrix will be happened. So around z axis, that means I need to consider on theta. So r theta equal to, because z axis I have said you right. So z axis means here this point will remain 1. So the parameter will be cos theta sin theta minus sin theta cos theta, because this rotation is a shift of clockwise rotation. And in the alpha means here around x axis. So x axis will be remain 1. And the parameters will be like this: cos, sin, minus sin, cos. Alpha is the parameter, and beta is nothing but it is around y axis. So y at y point, this place we will be having 1, and the remaining will be same: cos beta, sin beta, minus sin beta, cos beta 1. In this manner you are going to have the rotation transformation matrices. Right. So what is the next one? Finally, the transformation matrix for the sharing is given by. This sharing I have to discuss actually after the scaling operation. So in the time of scaling operation, I am uniformly scaling x, y as well as z. And finally, of course, it is, if I would like to have an homogeneous expression means I will be having in the form of a 4×4 matrix, which one the transformation matrix will be. So if there is a concept of sharing enters into picture, that means one will never be changed, the two other will be changed. That means the two other will be scaled up or down, one thing will remain constant. If that is the concept, that means sharing is happening there. So at the time of sharing discussion, the diagonal elements, as I have said you, they will be remained as 1. So now see here, the diagonal elements are remained as 1. So this is hxy, hxz, because x, y, z, and this is x, this is y, this is z. If I assume like this in this manner, this is x, this is y, and this is z. So the diagonal elements will be 1, and this location will be hxy, and the value of this location will be hxz, because it is in xth row and zth row. It is the intersection of xth row x, and row z. It is the intersection of row y and row column x, and it is the intersection of row z and column x. So in this manner we will be getting the sharing matrix, and finally the whatever the elements that are unused will be replaced with zeros. So this is the transformation matrix for your sharing operation. Now consider a concatenation of translation, scaling and rotation, that is about z axis for suppose. combined operation for this new point, that is old point. If I assume it as an P, the new point is given by P star. So what is this new point P star now? Okay, let me give you one example here to visualize this statement. We take two different affine transformations here, because in the time of explanation of the affine transformation, that means TRS, translation, rotation and scaling, what is the correct order we need to maintain, we should know, as I hadn't discussed it there. So in the affine transformation, let us see whether it is a commutative or not. Okay, so vector A bar is there initially. This is my vector A bar. Okay, this vector A bar is translated to a new point. So this vector A bar is translated to a new point here. Now we get a point, that is P1 equal to ATR. So what is happening here? This vector A bar is translated first like this. Yeah, it is translated. It is represented by A suffix T. It indicates it is translated. Now this translated vector is rotated by how many angular displacement, how much? Theta. Now it is a rotated version of the translated vector. So which is represented as A suffix Tr. This is my new point P1. That means here what I am doing here is I am making my vector to undergo both translation and rotation, right? So if first it went translation, next it went rotation. Now keeping aside this case, in the second case, my vector A bar is there. First it is rotated. That is why I am having a suffix here, A suffix R. After that it is translated. So it is translated means where from here this vector is translated. First it is rotated in this manner. Next it is translated. So ART. This is what I have got. That means the coordinates are being translated, are being shifted to some other new coordinate. This point is shifted to here and this point is shifted to here. So if we observe, this P1 and P2 are both same. The appearance is only different here. That means, can I say this matrix operation, the transformation of the matrix, the transformation matrix operation, will it be commutative? So that means here what we need to be cautious here is the order of the transformation also plays a vital role here. Why? Because whenever we are doing the affine transformation, that means we made a transformation like shifting, scaling, rotating, or shifting, scaling, or shifting and rotating, whatever it may be. It is a affine transformation. We need to follow a particular order here. What is that order here? First, for the affine transformation, translation of the point P have to come first. This is point P. Translation have to come first. Next, scaling have to come. Next, after that, rotation of the vector has to take place. This is the order of the affine transformation. So this R theta S T P, R theta S T is nothing but your transformation matrix. So R theta ST is nothing but your transformation matrix, which is nothing but affine transformation matrix. It is of size 4 cross 4. Okay. So this is about the affine transformation. Okay. So why we are studying these things is by using the affine transformation, it is becoming easier to understand the image formation in camera, which will be discussed later in our lectures. So, and also for understanding the perspective and orthographic projects, we need to also understand here the homogeneous coordinate system. Okay, that is why this is the main motto why we are converting an asymmetric expression of the matrix here into a symmetric expression. So we need to understand the perspective and orthographic projects, that means orthographic projections of the camera, which are discussed. So for understanding those things we need to know all the basic stuff. Okay, so here one example is there. A 3D object is there which is having the coordinates like this. It is simply a polygon, assume. Apply the translation, that means shifting here, which is distance 2 towards x-axis, 2 towards y-axis, 3 towards z-axis. So that means x-axis is translated by 2 units, y-axis is translated by 2 units, z-axis is translated by 3 units. So what will be the new coordinate system or new coordinates of the 3D space? So these are the given. The translation vector is, sorry, it is 2 comma 2 comma 3, not 1 comma 1 comma 2. So the new coordinate will be x nu, y nu and z nu. That means for A point I will be having A dash, for B point I will be having B dash, C dash and D dash. So the new coordinates of each and every point are traced out by using this expression, that is x nu equal to x old plus transformation along the x-axis, along the y-axis, along the z-axis. Finally this is the result of the new coordinates in the 3D space. So this is about the 3D transformations. Okay, so let me stop for here and we'll continue in the next session. Thank you. Have a nice day.